Hello, this is Group 7's dynamic programming video on the city grid problem. So the problem is where you consider you have a city whose streets are defined by a X and Y grid, and we're interested in walking from the upper left-hand corner to the lower right-hand corner. Unfortunately, this city has bad neighborhoods, and we want to avoid those intersections. So in order to work through the problem, we have three independent questions. The first is giving an example where there is no path to go from the starting intersection to the ending intersection without going through bad neighborhoods. Then there is to find a algorithm with time complexity xy to find a path across the grid while avoiding bad neighborhoods. And then the third question, which is to find an algorithm with time complexity xy to find the shortest path across the grid while also avoiding bad neighborhoods. So for question A, an example for a grid that has bad neighborhoods in such a way you have to cross them is any grid that has a line that crosses from end to end of said grid. So as you can see in the picture, uh, going horizontally across or vertically across means that there is no way to avoid bad neighborhoods, and going diagonally from the bottom left to the top right would also be a solution to question A. Now for question B, an algorithm to find a path across the grid while avoiding bad neighborhoods. We went with our answer is starting at the top left corner, check the neighbors of that intersection, and then check the neighbor's neighbor. Yeah, all the neighbors, essentially all the intersections two over from your starting position, and then moving diagonally down the graph where you can, so long as you won't end up in a bad street. And moving diagonally down and to the right will lead you eventually to the ending intersection. The time complexity in this case would be xy, because in the worst case, we would only have to check every intersection once. And this is the pseudocode for question B. You start at the top left corner at 0, 0. And then while you are not at the end intersection, so long as you are within the city grid, check to see if you can travel diagonally. If you can, then go to these cells and then just repeat until you reach the end. For question C, finding the shortest path, this is where we used dynamic programming. So for us, we found that the sub-problem would be at every cell you reach, you store the shortest path to reach that cell, and the process is repeated for every cell. So since we know how to get to that cell, because we've already stored the path, if two paths intersect, you can delete the longer path in order to get the shortest path that reaches the same place. And this is dynamic programming instead of brute force, because you are checking the first cell, then moving to the next cells available to you, and then doing checking for all of the cells available at, say, 2 steps. And then you repeat the process for 3 steps with all the previously saved paths to that would allow you to reach the cell right before those. You repeat the process until you get to the end. And since you're always storing the path to get to the cell you were just at, it's building off of saved subproblems. This is the pseudocode for question C. Um, you store all the paths in a dictionary, and then while we don't have a path to the target and intersection, you store paths to get to the next possible cell and assign cell coordinates. To, and then you check every time to make sure, well, you check every time to see whether or not you have gotten to the target and intersection. Now here is our toy example. So we have a 5x5 city grid from 0, 0 to -5, -5. And we have bad intersections from -2x and 0y to -2x and -1y. And then we have bad intersections at from negative from sorry 0x to -4y all the way to -3x and -4y. So for the steps, the way our algorithm works is that it doesn't necessarily go through the graph on a step-by-step basis, but rather determines the possible routes to take by recursively looking ahead from a cell to determine what the quickest path to that cell is. So it saves the paths and then it looks back at the saved paths that got it to the cell it needed to go to the quickest, or the next cell at least the quickest, and it built off that. And then we can have possible routes, like here in this example, where you can go back up over the bad intersection and around the entire graph. Uh, but in this case, the black route is 14 steps and the red route is 9 steps. Both are viable to get to the end, but because the routes intersect at the end, we first check the intersecting routes in order to discover the shortest one, and then we save the shortest route as the answer and delete the longer route. Our code is being implemented in VS Code using Java. Here's the code for our solution of the city grid problem. As you can see, we first create the grid in order to then add the data in later. We create the dictionary to store the shortest path and a parent here to store the previous cell. This is the starting point, and since it's where we start, it has to have no obstacle, so it's not a bad neighborhood we have to avoid. Here it goes through all the cells in the grid, skipping any bad neighborhoods and the starting cell. And then it checks from the top cell if the next cell is reachable and if the path is shorter, so should there be a conflict or a collision. And so this is the subproblem to minimize the path length, where it stores the path and the source, the previous cell essentially. Uh, And then here it checks to see if, or rather which uh, cell is a shorter path to reach the collision cell from. And then it stores the full shortest path to reach that cell. And then here, just in case, if the end is unreachable, then it just returns a null value that later on will output a no path found. In fact, it's right here. But first, it reconstructs the path from the end intersection or the bottom right to the start or the top left. And then this is where you add the data, your grid, where empty cells or good neighborhoods are zeros and bad neighborhoods are one. And then the target to reach is always this bottom right cell or bottom right intersection, I suppose. And here, again, if there is no solution, then it outputs that there is no path. Otherwise, it outputs the shortest path. And so here's it running. As you can see, based on our data, it starts at the top left, of course, goes to this intersection, down, over to the right again, and then straight down. And that is the shortest path while avoiding bad neighborhoods.